Welcome back, everyone. Today's video is going to be a relatively short video, which is mostly going to be about notation and how sets are often used as part of notation. So to start with, I want to remind you about sigma notation, which is something I'm sure you have seen before. And so here is an example of sigma notation. And remember, the sigma here is a giant Greek S, so it means to take the things here and sum them. And by the things here, what do I mean for I squared? Well, the sigma notation says start at I equals 1 and then work your way up to I equals 5. So you'll get 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And so sigma notation here is just a way for us to write this out more compactly. Now, I'll note there's a lot of variations of how sigma notation is used. So, for example, often instead of writing out the I squared here, we might do something like create a sequence where the nth term is n squared. And then you could write this same thing up here as the sum. So I goes from 1 to 5 of ai. All I've done here is give the terms here a name. So little ai is just the name for the ith term. So little a1 is 1, little a2 is 4, little a3 is 9, and so on. And so then I could write this same sum in this fashion. So these are both ways of writing the same sum. Now, so far there's no sets involved, but really what I'm describing with this I equals 1 and 5 is that I'm really summing over i's in a particular set. And so I could write the same sum, and this is how mathematicians will usually write this, as being the sum across I in the set 1 through 5 of a sub I. And so what is this here? This is just indicating, take the sum of a sub I, that is the thing given by this formula over here, as I ranges again across the elements of the set 1 through 5. This is particularly nice if you want to talk about something like the sum as n goes from 1 to infinity of 1 over n squared. So this was this famous sum that you talked about a lot in Calculus 2, that this is a p-series for p equals 2, so it converged. And in fact, your professor might have told you it converges to pi squared over 6, or whatever. But this sum you could also describe as the sum across n in the positive integers of 1 over n squared. Again, this is just saying, plug every n in the positive integers into this n and add all those things together. And so most of the time, outside of calculus courses, when you see someone write down a sum, whether it be a finite sum or an infinite sum, and they're going to use sigma notation, they're usually going to write it as the sum across and then the indices in some sort of set. And then they'll describe this in some capacity, which may be written actually in the sigma like it is here, or they may give it a name outside of the symbol. So let me make an obnoxious question, because I always like obnoxious questions about the empty set. What is the sum across n in the empty set of 1 over n squared? And it probably takes a moment to decide, because sort of in some sense, this doesn't make any sense, because you can't add 0 numbers together. In fact, even in a certain sense, you can't even add 1 number together. Like, what is even this supposed to mean? And we do agree that even though there's nothing to add here, I think the only reasonable answer here is that this is a ninth. In the same way, we make the agreement that if you're going to add something over the empty set, that is, if I add 0 things together, what am I going to get? We make the agreement that the answer here is 0. Now, this choice of 0 here is going to connect back in a moment to an explanation of something I often get asked about, which is this bizarre choice that mathematicians always say that 0 factorial is 1. And I want to think about, in a moment, why I should say 0 factorial is 1, whereas this sum is 0. And I'll talk about that in a moment. But before I talk about that, I want to note that this whole notation for repeated sums, I can do this same idea for other operations. So just in the same way I could do repeated addition, I could also do repeated multiplication. When we want to talk about repeated multiplication, instead of using a capital sigma, which would stand for sum, we use a capital Pi, which stands for product. Okay, so this is intended to be a capital Pi or a big pi. And so what is this telling us? This is telling us start at I equals 1, plug each of those things in here, and multiply them together. So in this instance, if I plug in I equals 1, I get 2. If I plug in I equals 2, I get 5. And if I plug in I equals 3, I get 10. And I'm supposed to now, because this is a pi, multiply these together. And so that is to say I would get 100. Now, sometimes instead of explicitly writing a set here, sum across P and S, sometimes just describe the set the same way you would in set notation. So in this case, you might say something like the product across P prime, where P is less than 10. And so this is describing for you to take the numbers 2, 3, 5, and 7 and multiply them together, which will give you 210. This is another variant of the same notation. Again, capital Pi is a product, capital Sigma is a sum. And so you'll see stuff like this, the sum across P prime of 1 over P, which would be 1/2 plus 1/3 plus 1/5 plus 1/7, and so on. And it happens that Euler proved that actually if you do take this sum, it actually diverges. So if you're curious, in fact, this works out to be infinity. But the emphasis for this video is just on understanding why this string of symbols equates to that. So what is n factorial? Well, n factorial is a repeated product. It is the product of all I as I goes from 1 up to n. Or if you prefer, it's the product across I in the set 1 up to n of I. These are different ways to write the same thing, and this is exactly the definition that you're probably used to of n factorial, just written in a notation you probably haven't thought about before. Namely, this is saying take the product 1 times 2 times 3 times 4 times 5 up to times n. Now, once I agree that this is what I mean by n factorial, then when I write down 0 factorial, I'm sort of priced into what that's going to mean. Well, that is going to mean the product across, and so if I write down all the numbers from 1 up to 0, well, that's not actually any numbers. This is going to end up being the product, really, of I in the empty set of I. Now, this is intended to harken back to what we said about empty sums. Namely, we agreed, or at least I told you the convention is, that an empty sum is 0. And in fact, if you ask most people to guess, what should 0 factorial be? Almost everyone will tell you as their first guess that 0 factorial should be 0. And their intuition is probably coming from something like this, like there's nothing there, so I should get 0. But unlike an empty sum, where our convention is that the answer is always 0, for an empty product, our convention is that the answer is always 1. And so I want to emphasize here, this is not something specific to factorials, rather it is a more general convention that every empty product is 1. And what do I mean by an empty product? I mean a product over elements of the empty set. And so this is just an agreement we make that every empty product is 1 and every empty sum is 0. Now, at first, that's maybe a ridiculous convention. Why the difference? Why is one of them 1 and why is one of them 0? But the answer is actually related to the operation. Namely, this 1 here is what we call the identity of multiplication, and the 0 here is the identity of addition. Again, 1 is the identity of multiplication, because everything times 1 is, well, whatever the everything was. And 0 is the identity of addition, because anything plus 0 is, well, it's that same thing again. Now, of course you could just believe me. Okay, so that's the convention. So 0 factorial is 1 because it's an empty product, and then move on. But it's perfectly reasonable for you to say, wait a minute, why should I want the identity of the operation to be the thing I choose in my convention? Why not just choose that every empty sum, product, whatever, why not choose just that every one of them is 0? So, let's drill down. So I've written here 3 different sums. So one here, I'm summing across all the elements of some set that I've called capital A. Another, I'm summing across all the elements of some set I've called capital B. And in a third, I'm summing across all things in A union B. What do I want the relationship between these 3 things to be? Well, I think it's pretty reasonable to say that I actually want it to be true that if I add all the things in A and all the things in B, that I get the same thing as if I add the things in A union B. That is, I want this to be true. Now, unfortunately, this isn't quite true, and if you squint at it for a second, you'll realize why. And the reason why this isn't quite true is that A and B might have elements in common. But here's what's actually true. If A and B are subsets of R, and we add this annoying piece that they have no elements in common, then if I add all the elements in A and all the elements in B, that's the same thing as adding all the elements in A union B. Now, of course, I want the same thing to be true for products. Namely, I want it to be true that if I take the product across n in A and I multiply that by the product across n in B, then I get the same thing as if I take the product across all the n's in A and B, or in A union B if you prefer. And my point here is this theorem should really almost be a tautology. That is, it should really be something that's just true by definition, because on the left-hand side, I'm saying I'm adding all the things that are in A or B, and I'm saying exactly the same thing on the right-hand side. And ditto down here. Again, I'm saying I'm taking the product of everything in A and in B. Well, that's almost exactly the same thing I'm saying over here. So what does this have to do with empty products or empty sums? And here's what it has to do with empty products and empty sums. Namely, I'm going to take these 2 formulas, and I'm going to plug in the set B equal to the empty set. In the first line, what am I going to get? I'm going to get the sum across n in A of n plus the sum across n in the empty set of n is equal to the sum across n in A union the empty set of n. I can simplify this piece a tiny bit because A union the empty set is just A. So this will be the sum across n in A of n plus the sum across n in the empty set of n is equal to the sum across n in A of n. But now this and this are the same, so I can subtract them from both sides. And when I do that, what am I left with? I'm left with that the sum across n in the empty set of n is just 0, right? I just subtract this thing from both sides, cancel it or whatever, and I get that the sum is supposed to be 0. And so is this a proof? Well, not really. What is this? This is really an argument that if you want to define a sum over an empty set, the only reasonable choice for what that sum over an empty set should be is that it should be 0. Again, intrinsically, summing over an empty set is utterly meaningless. It's saying take the sum of all the things in here, but there's nothing in there. Who knows what you're going to get? But if you have to pick something, this basically tells you, okay, well, if I'm going to define this to be anything at all, I'd better pick 0. As you might predict, if I plug in B equals the empty set here, that will help explain why the empty product is supposed to be 1 instead. Namely, if I plug in B equals the empty set to my equality, I get this, which is ultimately going to give me this. Again, just like before, this and this are exactly the same thing. So just like before, I can cancel them. But there's a difference between this and the last page. Namely, here, the operation is multiplication instead of addition. So when I cancel these, I'm not subtracting like I was up here. Instead, when I go to cancel the two things in the blue boxes, I'm dividing. And so when I divide both sides by the product across n and a of n, what I'm going to be left with is the product across n in the empty set of n is equal to, but now this product divided by itself is not 0, it's 1. And that in turn tells you that an empty product, if you want it to make sense at all, had better be equal to 1. Otherwise, it's not going to really work with what you're talking about. And this is at least a very highbrow explanation of why it is that 0 factorial is equal to 1. Now, if you're the sort of person who would prefer a much lower brow explanation, you might, for example, look at Taylor's theorem, which tells you the formula for a Taylor series, and you might note that if you chose 0 factorial to be anything other than 1, that the formula would have to have some weird exception for the 0th term, and so you just make life cleaner and easier if you would do indeed choose 0 factorial to be 1, but I at least find this argument more compelling. So now, why did I really bring all of this up? Is it really this connection to sets here? Well, partially. But the other reason I bring this up is that addition and multiplication aren't the only operations that you'll often want to do repeatedly in the way that I've done with sigmas and pi's here. The other two operations that you'll often see repeated using almost this exact same notation are union and intersection. So let me give you a sense of what that would look like. So here, for example, we have a union, as n goes from 1 to infinity, of the set of integers from 1 up to n. And so what does this mean? Just like the sigma or the pi, this is telling us to take 1, but now the operation is literally union. 1, 2, union, 1, 2, 3, ... and keep going like this forever. And what set do we get if we do in fact take this whole union? Well, if we do in fact take this whole union, then we will get z plus. That is, eventually, every positive integer is in one of these sets, so if I take the union of all of them together, I get all the positive integers. What if, on the other hand, I take, say, the intersection across n and the positive integers of the closed interval from 0 to 1 over n? Okay, what does this mean? This is saying take the interval 0 to 1, intersect it with the interval 0 to 1/2, intersect it with the interval 0 to 1/3, and so on. And what am I going to get? That is to say, what thing or things is an element of every single one of these sets? And this might take you a bit more time to think about, but in fact, only one single real number is in every one of these sets, and that single real number is the real number 0. And so, in fact, the intersection of all of these is the singleton set 0. Now, if you remember how at the beginning we sometimes took a little a sub n and wrote down a formula for it and then used that in place of the actual formula itself, we'll sometimes do that with sets, too. So I might take, for example, ai to be the set I minus 1, I plus 1, in which case, for example, a5 here would be the set 4, 5, 6. Again, just plugging in the formula. And so then you might, for example, ask, okay, what's the intersection across all I and z of a sub I? And what's the union across all I and z of a sub I? And I'd encourage you here to pause for just a second and think about what these should be, just to make sure you're following along. So, this is the intersection of all of these sets. What is in all of them? Well, nothing is in all of them. this is the empty set. How do I know that? Well, I wrote down A5 for you. It has 4, 5, and 6 in it. I could just as easily have written down A0, which would be -1, 0, and 1. And if you look at the intersection here of -1, 0, and 1, and 4, 5, and 6, there's already no elements in common between these two sets. So if I throw in a whole bunch more sets into the intersection, there can't possibly be anything that's left. So this is the empty set. On the other hand, what am I going to get if I take the union of all of these for all i's? Well, here, I'm going to get z. How do I see that? Well, as with all equalities about sets, what I really have to argue is mutual inclusion. That is, I have to say every element here on the left is an integer, and every integer is an element of the union on the left. And both of those are actually pretty straightforward once you understand what these symbols are saying. So why is every integer in this union? Well, take your favorite integer I. Well, I is an element of AI, so it's in this union. On the other hand, every element of any AI is going to be an integer, and so that means everything that ends up in this union over on the left-hand side is also an integer. So when you see this kind of notation, this is all that's really going on, and we're not going to use this notation very much throughout this course. I'm mostly putting this video here to prepare you for the fact that you're likely to see these kinds of things in other courses, particularly if you take something like real analysis or topology or some of our other courses, you're likely to see this kind of thing pop up. But that's all for this video. In the next video, we're going to start talking about functions, which is going to be one of the most important topics we talk about and is going to tie everything we've done so far and will do in the future together. So, rest up, and I'll see you next time.